Professor R. Ashokamani, Director for Research and Development, Dhanalakshmi Engineering College, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome you to the UGC lecture series on applied electronics. In this paper about which I am talking about is on physics of materials, and we have been going through a course of lectures on crystal structure. In this lecture, we will be having the following contents: characteristics of cubic lattices, hexagonal close packed or HCP structure, the formation of HCP and FCC structures, the CBA value for the HCP structure, and the atomic packing factor for the same structure. I now show the crystal structures of some of the metals. In the earlier lecture, I was discussing about cubic lattices. Now, what are the 3 cubic lattices? It is simple cubic, body centered cubic, and face centered cubic. What do you find here? You find here a body centered cubic structure, the unit cell of a BCC unit cell, you see, right. You have got atoms at the corners and you have got atom at the center. You see here a red circle atom at the center. This is the body centered cubic unit cell. As I mentioned to you some time back, iron is one of the examples. Iron is crystallizing in this structure. Okay. You have in this building, we have got iron rods, the whole building. Any civil structure is made up of steel or iron with carbon and steel, but iron has got a body centered cubic structure. Now, when I say that iron is having BC structure, do you believe in me, or how will you ensure that it is crystallizing in the structure? What kind of experiment you will be doing? You can even do a quantum mechanical theoretical calculation to determine the given structure of a solid. Given a solid, what is the structure in which it should be crystallizing? You know 14 types of crystal structures, in which structure a solid should be crystallizing. Iron should necessarily crystallize at room temperature and at ambient pressure only at the body centered cubic structure. This can be experimentally determined by X-ray diffraction, as I told you earlier in the lectures on bonding. You know, the bonding and structure, they are intimately related to each other, and so iron should be crystallizing in the body centered cubic structure. Whereas, you find lots of elements in the periodic table, such as nickel crystallizing in the FCC structure. This is the what is called the unit cell of a FCC structure. This is the FCC unit cell. You see here atoms at the corners and then the atom at the face center. This is a body centered cubic structure. This is what I am showing here. On the other hand, I showed you some time back atom at the center of the faces, that is the face centered cubic, right. You find here atom at the face center. For this face, you got an atom here. This is a structure in which very many elemental solids are crystallizing. Take for instance, the metals like copper, nickel, palladium, strontium, very many metals crystallize in the face centered cubic structure. You find atoms at the corners and at the center of the faces. Here you got atoms at the corners and the center of the cube, in which iron is crystallizing. Again there are a number of other solids crystallizing in the body centered cubic structure. Let us now pass on to understand in a holistic manner the various characteristics of cubic lattices. Here I give the summary of the various things, the volume of the unit cells irrespective of whether it is simple cubic, body centered cubic or face centered cubic, they are all after all cubes. So, the volume of the unit cell should be same, a cube. The number of lattice points which could be associated with simple cubic is 1, body centered cubic it should be 8 into 1 by 8 plus 1, 1 plus 1 2, whereas in the face centered cubic you have got 6 faces and 8 corners. The contribution coming from 8 corners will be 8 into 1 by 8. Face center is half, 6 into half. So, 1 plus 3 4. So, the number of atoms associated with every FCC unit cell will be 4. The volume of the primitive cell is given here 1 by a cube, 2 by a cube, 4 by a cube. Coordination number is nothing but the number of nearest neighbors. The number of nearest neighbors for simple cubic it is 6. For body centered cubic obviously you can take this as the reference atom, the number of nearest neighbors is 8, right. You have got an atom here, the nearest neighbors you find here, 8 will be the number of nearest neighbors for body centered cubic. For face centered cubic it will be 12, right. The coordination number for FCC unit cell is 12. It may be difficult for an young student to visualize or to understand how the coordination number is 12 for face centered cubic. Now, having got the model for a face centered cubic, now let me try to make you to understand how you get 12. You take this atom as the reference atom, right. You have an atom here, atom here, atom here, atom here. How many atoms? Mean the number of nearest neighbors. You got atom here is nearest neighbor, right. Then second, third and fourth, then fifth one, right. The distance between this and this will be same, sixth one and seventh one, and you know you got atom here, and so any atom that connects this atom with the how many face centers, the nearest neighbors you got one face here, second face, third face and fourth face, right. This is the origin, you have got in the same plane you have got 4 atoms, right. Then there are 4 face centers, right. This is the origin, there is 1 here, 2 here, 3 here, 4 here, all of them will be equidistant. This distance as well as this distance and this distance will be same. Okay. Then the important thing is there will be an adjacent cell, right, adjoining to that there will be another cell here. For this cell also there will be all are face centered, for this cell also there will be an atom here, atom at the face center, atom at the face center. Okay. So, you know for this atom I will be having one atom here, second atom here, third atom here, fourth atom at the this face center, similar to what I have here. Now, I think you should be able to understand how I get 12. It is generally people find it difficult to understand how the coordination number of FCC is 12. So, one should have in mind for any given atom at this face the same plane there are 4 atoms, then at the face centers you got 4 atoms, the from the adjacent cell at the face center there will be another 4 atoms. So, all of them will be equidistant, that is how you get 4 from the same plane and 4 from the same cell, the atoms at the face centered positions, then there are 4 atoms from the adjacent cell again at the face centered positions. So, 4 plus 4 plus 4 makes 12. Now, this is somewhat difficult for beginners to understand as to how you get 12 as the coordination number for the face centered cubic structure, or 12 as the nearest neighbors or coordination number for the face centered cubic structure. The nearest neighbor distances are a obviously for simple cubic root 3 by 2 into a, and similarly a by root 2 for the face centered cubic. The packing fraction, the values are tabulated. This is what we calculated in the previous lecture, namely 0.524, 0.68 and 0.74. The most important thing to be noted is FCC has got a highest packing fraction, right. The highest packing fraction has potential significance. I will come to that at a later stage. The 74% of the cell volume is occupied by the atoms. I will call this as the space filling principle. What is the subject we are dealing with? It is called condensed matter. You know, I told you in the beginning, the origin of the universe, you started with plasma, then what? Then you have a gas, a liquid, the liquid got into the condensed state. This is called the condensed matter physics, CMP. That means, you know, any system tries to occupy maximum space. It is called a space filling principle, a very important principle. And so, the space filling, the atomic packing fraction calculation is important. The highest packing fraction is of practical significance, and I even tell you foretell, or even I am telling you even at the beginning, the highest packing density is preferred by most of the materials. So, most of the materials will try to go to this particular structure, namely 0.74, that is the packing density having 0.74. Let me now check among the other 14 lattices, is there any other lattice having the packing density having a value like this or higher than this. Okay. If there is a material, if there is a structure having a packing density higher than this, then material has a tendency to go to that structure. Okay. The APF value has got a very important significance. With this, we close the discussion on cubic lattices. Let us now pass on to another lattice structure, namely this is called the hexagonal closed packed structure, HCP structure, hexagonal closed packed structure. Now, what do you observe here? You have got a plane here, right, wherein you have got an atom here, it is hexagon, you see a hexagon, right, what atom here, it is called hexagonal closed packed because you have got atoms at the hexagon here, then another hexagon here. Supposing the you have got atoms here, these 3 atoms would have been missing, it is called simple hexagonal structure. Can you tell me an example of a simple hexagonal structure which is used as a lubricant? There is a hint given. Graphite is a material crystallizing in the simple cubic structure. You know, the bonding in graphite is you know, the van der Waals bonding weak, van der Waals bonding, you do not have 3 atoms here, right. You have got atoms here, right, and atoms here, the carbon you have here, right, carbon atoms, and the top plane, the bottom plane, the mid plane will be absent. The atoms carrying 3 planes is called the middle plane, that will be absent. If that is so, it is called a simple hexagonal structure. Graphite is an element crystallizing in the simple hexagonal structure. Because of the absence of these 3 atoms, the bonding will be weak, because the distance that separates the 2 atoms is very large, the bonding will be weak. So, the layers can easily slide one or the other. Okay. The layers can easily slide one or the other. The bonding is the van der Waals bonding, because of sliding, you know, the grease or whatever that you got graphite acts like a lubricant. Graphite is a example of a simple hexagonal structure, and an example for a solid in which you got van der Waals bonding. Apart from having atoms at the top plane and bottom plane, If you have got 3 other atoms at the mid plane, it is not a simple hexagon, but it is a hexagonal CP, hexagonal close packed structure. Okay. Cobalt is an example. Now, this is structure in which the ferromagnetic material cobalt is crystallizing. You know, I told you some time back, iron crystallizing in the body centered cubic structure, cobalt is crystallizing in this structure, whereas nickel, another ferromagnetic material, will be crystallizing in the FCC structure. We will have a short break at this point. We will resume with the rest after the break. Welcome back after the break. As I got a model for the HCP structure, let me try to explain in a more clear fashion the arrangement of atoms in the HCP structure, right. First of all, I will ask you to forget about the plastic thing that you have got in the center, that is nothing connected with it is no way connected with the HCP structure. That is one about which you should be focusing your attention when you talk of Brillouin zones in the chapters to come. I will be talking about Brillouin zone when you want to determine the energy of the electron in a solid or the energy of phonons in solids, right. In this chapter itself, I will be mentioning about phonons. Now, when you want to calculate the energy of the phonons, you will be talking about Brillouin zone. This is the Brillouin zone. Let me not go into details about the Brillouin zone, we are not concerned about it at present. Let us look at these spheres, right. You have got unfortunately, you have got the broken atoms, and so each sphere, the green sphere that you have got here, they refer to you, this is the mid, this is the top plane, you have got atom here, right. The atom at the center, you have got atom here, right, and then 1, 2, 3, 4, 5, 6, right, is the top plane. There is identical bottom plane, right. This is what you have got. Okay, you got atom at the center. Now you got atom at the center, and then there are 6 atoms surrounding that. That is what is shown here also. Then there will be 3 atoms in the middle plane. Where do you find this atom? It is from the centroid. You will have a triangle. I will show the triangles later. From the centroid of a triangle here at a distance of c by 2. What is c? C is the distance that separates the top plane and the bottom plane, right. The c axis, and this is called a mid plane. At a distance of c by 2 from the bottom plane, you have got 3 atoms, we call it the mid plane. So, you have got 3 atoms here in the middle plane. So, unfortunately, they are sticking here, but the point is that be 3 atoms, not exactly they will be at the centroid of they will be separated by obviously by 120 degrees, right. Each atom separated by an angle 120 degrees. There will be 3 atoms at the center. That is all I have to talk about this model, that is using which you can try to understand the HCP structure, that is a solid like cobalt crystallizing the structure, and maybe many solids like magnesium, right, and many systems, technetium, magnesium, and zinc, and cadmium, they are all crystallizing in the HCP structure, okay, the hexagonal close structure. And you should remember there is only one lattice parameter in the cubic structure. In the cubic structure, irrespective of the fact whether it is face centered cubic or body centered simple cubic, there will be only one lattice parameter A, right. The cube has got only one dimension, because in the cube all sides will be equal, but here it is a hexagonal structure. Therefore, there will be 2 lattice parameters, there will be C here and A here. What is A? A is the distance that separates the 2 atoms here, the distance between these 2 is A, again these 2 is A, okay, obviously. Then this distance is much higher, right, this is C and this is A, and now let me proceed to find the ratio of the 2 values C by A, right. what is the magnitude of the C, and you have got A here, the C by A value we have to calculate, and that is what we have to do now. Now, prior to going to find the C by A value, let us now try to understand how we get this structure, namely the FCC structure, and similarly how we get the HCP structure. Now, what I would like to do, maybe the youngsters like you, what you should do is you get a few tens of balls, maybe you can take broken table tennis balls. You are having, supposing I give you say 100 table tennis balls, I will ask you as to how you can keep the 100 the table tennis balls and stack them. What are the possible stacking sequences? I am going to talk to you about there are only two possible stacking sequences, the way in which you have the first layer, second layer, third layer, fourth layer. The two possible stacking sequences are the two ways of arranging the billiard balls or table tennis balls one over the other, right. One arrangement is like this. You look at the bottommost layer, this is the bottom. I put that my table tennis balls, one ball here, another ball here, another ball here, another ball here, and so you try to place the balls, right. 20 balls, I have the balls here, right. Every green circle refers to a ball, right. They are placed side by side. They are placed side by side because it is a hot sphere model, they are touching each other. As I told you in the earlier lecture, the atoms are looked or being considered as hard spheres touching each other, and so the atoms are made to touch each other. Okay. I have arranged the atom like this, right. It is a basal plane. Okay. Then you look at a point like B. Where do you find B? The B sides, B is here, right. You have got green, which refers to the bottom plane, right. The atoms are the basal plane. Okay. The B sides are shown by the blue colored rings. You see the blue colored ring, and so at the center of at this point you place the second layer, and the ball, the remaining billiard ball or the table tennis ball, you find the stacking sequence. You are putting you are generating the second layer. What you do is you are at this point, there will be some 3 balls are sitting, 1, 2, 3 balls are sitting, then obviously there will be kind of surface in which easily you can fix the ball B, right. When you got 3 balls, there will be some sort of hole above which it will be easier to put the ball B, that is the second layer. By placing the B's together, B here, B here, where do you put the B? At the junction where the 3 balls meet, right. Okay. B here, and you got 1, 2, 3, B here, 1, 2, 3 here, B here. So, these things are B, right. So, the B sides, how do you get by B sides? You are placing the second layer, that is the second layer forms the B side. Then you look at the C side. The C sides are indicated by a different color. Above, after having constructed a second layer, you think of the third layer. The third layer will be looking like this, right. The third layer that you have got here will be above the thing, this one, and so this is the third layer. The C site is here, right. B is here, above the thing there will be these are the points above which you will have the third layer. So, if the layers are built, the A layer, that is the bottommost, then the second layer is the B. The third layer will be different from the second layer, the arrangement of your balls will be different from that of the second, again different from that of the first one. So, this you have to do for yourself, you can go home and do it leisurely, that will be forming the third layer, that will be different from the first one and the second one. So, the stacking sequence if you have got A, B, C, then again you have the fourth layer corresponding to the first layer, corresponding to first layer, then you will be having the fourth layer. So, then again you repeat A, B, C, again A, B, C. If this kind of arrangement is done, then what you will be obtaining is the so called you got atoms at the corners, then atoms at the face centers. You got atom at the center of the this phase, center of this phase, and so on. It is FCC unit cell. What I would like to tell you is this kind of stacking sequence, wherein you have the bottom layer made up of the green circles, the bottom layer, the atoms or the billiard balls being arranged right, the bottommost plane, that is A, corresponding to this thing you have the second layer, corresponding to these points you have the C layer, the third layer, right. If this A B C is again repeated, then A B C, again A B C, and so on, first layer, second layer, third layer, then first layer, the first layer and fourth layer will be identical, second and fifth will be identical, third and sixth will be identical, A B C, then A B C. This kind of stacking sequence will give rise to what is called FCC structure. If you look at in every region, we will be looking like this. This is one kind of packing, that is how one gets the FCC unit cell. Then there is yet another way of arrangement, right. Another way of arrangement is the following. You have in the green region, the green is the bottom layer, okay. Then you got a top layer is again green. You should remember the bottom layer is green and the top layer is again green, and these two colors are matching. So, the bottom layer is here and the top layer also is the same, right. This color you have here, this color you have it here, the bottom layer and the top layer one are the same, but the middle plane, the B sides, the middle layer you place an atom or a ball at this trijunction. You got 1, 2, 3 atoms joining each other, and on this you are putting the second layer, right. The remaining balls are kept here, and you place another ball here, another ball here. So, having constructed the first layer, how do you construct first layer? You are putting the balls side by side, okay. In whatever be the way in which you are putting, it will lead to automatically, when you are close packing, it will lead to a shape like hexagonal shape. And then the one arrangement, as I told you earlier, the second arrangement, the possibilities, you have to have necessarily the atom, the middle layer will be here, then there will be a ball which can be kept above this, a ball which can be kept above this trijunction, that will give rise to the middle plane. So, if this A B A B A B if it is repeated, then that will give you hexagonal closed structure. The most interesting thing, it is have been given in the slide, the APF is 0.74, which is similar to that of the face centered cubic structure. So, the wonderful thing is I told you the significance of the value number 0.74, that is the packing density. The packing density, that is the atomic packing fraction, is 74% for FCC, and this slide shows the packing density for HCP structure is again 74%, exactly identical to that of FCC lattice. This is again a very significant observation. Now, we will try to find out how you arrive at this 74%. Now, before that, in every, when you calculate the packing density, packing fraction, first you go to the coordination number, right. What is coordination number? The number of nearest neighbors. You take this atom as the origin. How many nearest neighbors are there? The top plane is a hexagonal plane. So, there will be 6 here, right. Similarly, if you take any atom here, that will be surrounded by 3 atoms that you have got in the middle plane, then 6 from the top plane and 6 from the bottom plane. So, the coordination number will be for any atom here, there will be 6 from the bottom plane, 3 from middle plane, 6 from the top plane, right. So, anyway the coordination number will be 12. Okay. Let us see the details in the slides to come. The coordination number, you take this atom, the coordination number for any atom, because you know it is a repetitive pattern, it will be 12. Important point is again the coordination number of FCC is also 12, right. What is the coordination number for FCC is 12. Okay. That is important. The coordination number for a FCC is 12, the coordination number of HCP is 12, the packing fraction of FCC and HCP are again 12. Okay. And these are some of the important points. Let me now try to summarize the points which we have understood from this lecture. Many elemental solids crystallize in FCC and HCP structures. The stacking sequences of FCC and HCP, they differ. Both FCC and HCP structures have the same coordination number. We will pass on to the question session. We have the following questions to you. Number 1, comment on the coordination number and nearest neighbor distance and the packing fraction of FCC and HCP structures. What are the two most favored structures in which solids crystallize? With this we come to the end of this lecture, and the rest of the things we will see in the lectures to follow. Thank you.